Okay. Again, it's going to be a lot of me talking, but lots of interruptions with cool stuff. Components of the universe. The biggest thing, galaxies. Actually, there's something called galactic clusters, which are clusters of galaxies. But then galaxies, zooming in from galaxies. We did end last day, Hudson, talking about star clusters. So I guess that's the next small thing. Groups of stars that aren't big enough to be a galaxy, but they're kind of hanging out together like a neighborhood. Stars is the next smallest thing. Of stars, planets, black holes, and the unimaginably huge distances between them. What's a star? Basically, a star is a nuclear reaction in space. It's a fusion reaction. A nuclear reaction in space. Stars are made of hot gases that are reacting to give off heat and light. They don't actually burn, even though we talk about the sun burning or the star or stars burning. It's not a flame per se, it's a fusion reaction. But if you want to imagine that they're burning, go ahead. I'm not going to freak out about that, Nicole. The sun is a star. I don't know if you remember the first time you realized that. Usually you're about 8 or 9 and suddenly you go, really? The sun is a star? You mean this thing, there's all those little dots are the same as this big thing that gives us, wow, gives us all that light? We think it's special, but actually it's really just a very average star, which is a good thing, because it seems that very average stars give us nice conditions for life. If it was an unaverage star, probably not. I said average star. That suggests that there are different types of stars when there are. Stars vary from small to huge. Smaller stars, like our sun, live much longer. And in fact, the size dictates their life cycle. One of the things I am going to be asking you to learn, Riley, is the life cycle of stars, the steps. There's 7 steps before that goes from kind of birth to no longer. Not only do they vary in size, stars vary in color. Red is coolest, blue is hottest, just like flame. Hopefully you've learned that a blue flame is much, much hotter than a red flame. If not, now you know. How could I try that? Stick your finger in it. Well, no, maybe there's a better way to figure that out. Okay. So they vary in size, they vary in color, and then there's a third thing, they vary in brightness, except there's a fancy word. Don't write the word brightness. The fancy word is they vary in luminosity. How bright they are. So, an average or intermediate star has a life cycle. Looks like this. So you have 7 little blanks there. And I've got a little color picture. The first thing that happens is a nebula collapses. So that's the word that goes in the blank, but I want you to write in brackets, draw an arrow pointing to the word nebula, and you can write next to it, star nursery. It's really where stars are born. A nebula is a huge cloud of dust and gases and other material. How huge? Think many, many times bigger than our solar system huge. Those are the building blocks for the stuff of the universe. I'll let you fill in the blanks, and I'm going to talk about what each of these mean. And I have a video that shows it too, but it's worth repeating. So, it turns out, yeah?
I think this one is in size dictates the, what is it?
Life cycle.
Oh,
This is the life cycle of an intermediate star. The life cycle of a small star is actually different because it ends up in a different thing. The life cycle of a large star is different. It ends up becoming a different thing. And I realize I used the word thing in very generic on purpose. So, you ready? Here's what happens. You have a nebula, all this dust, slowly, because all the dust has mass, gravity pulls the dust in. Over millions, over hundreds of millions, over billions of years. Okay? When you have enough of this dust and gas and material, because the gravity pushes down on itself, it starts to form a ball, and in the center of that ball, pressure is tremendous. Tremendous pressure. How much pressure? It actually starts to create heat and fuse atoms together. That's step 2. You get a self-sustaining reaction, and lo and behold, a star is born. It starts to give off heat and light, instead of just being a cloud of gas. Then you have the main sequence stage that lasts for a few billion years, and I say that very casually, a few billion years. It lasts for a while. But the way a star burns, the way the star the nuclear reaction occurs, it uses hydrogen. Element number 1 on our periodic table, 1 proton and 1 electron, the simplest element. And it's using that up, it's fusing those into other elements, which gives off heat and light, but it's using up its hydrogen. Eventually, it starts to run out of hydrogen. When that happens, the pressure inside actually causes the star to expand. So step 1, nebula collapses. Here's your star, the main sequence stage. Then when you start to run out of hydrogen, you start to expand into a red giant because you've run out of hydrogen materials to sustain a normal fusion reaction. Often it gives off a lot of its outer shell. It doesn't explode, but it gets rid of a lot of its outer shell, which is good because that gives us the building blocks for life. Then, after becoming a red giant, it collapses into a white dwarf, which is a colder, smaller version of the star, very dense. And then it collapses into a black dwarf, not a black hole, a black dwarf. What do all these mean? I think I have a video here. Oh, pictures first of all. So here is a nebula. This is the nebula of Orion. This is a star nursery. Stars are being born here. A few billion years from now, that will look very different if you hang around. Preview of coming attractions. The Trifid Nebula. Stars are being born here. It's a cloud of gas. You can start to see that little bright area right there. Ah, some stars are starting to form already. So, formation of a star. Let's go in more detail. All stars form in nebulas. By the way, really the plural of nebulas is nebulae with an AE, but I didn't want to scare you. Clouds of gas and dust, mostly hydrogen. When gravity causes some of the cloud to come together. You write that down. Write that down, right? And it forms a mass called a protostar. That's a word you're going to need to know. A protostar is a pre-star. Hasn't formed a star yet, but it's getting close. And in this protostar, Amelia, gravity is pulling it in, and so in the very center, pressure is increasing tremendously. And because pressure is increasing, it's also heating up tremendously, and atoms are being squeezed together tremendously. As the protostar gets bigger, the temperature increases to about 10 million degrees. And hydrogen atoms fuse, forming helium. By the way, the word helium is from the Greek word helios, which is the Greek word for the sun. The first place that they discovered helium was in the sun. Then they found it in the earth, but back in the, I think it was the 1850s when they were, the sun has this element called helium. This is now a star. Light and heat are being given off. And this reaction continues for millions, even billions of years. A long time. So let's talk about what's going on inside this star. Hydrogen fuses. No, let me just double check. Oh, I did. Good. Hydrogen fuses to form helium, and when it does that, it releases energy, light and heat. Eventually, the helium builds up, and it starts fusing to form even larger atoms. And the process continues. You guys can turn the page over, but I don't think I put this next part in your notes. I just want to walk you through it. So remember our periodic table? What was the first element? And if you're not sure, it's back there. So here's what's going on inside a star. It starts out with a hydrogen atom, which is one proton, and another hydrogen atom. If you squeeze, and we can do this in a lab, but we use a lot of energy to do it in a lab. Stars do it naturally. If you squeeze one hydrogen, one proton, and one hydrogen, one proton, how many protons will you get? Not meant to be a trick question. How many protons will you get? 2. Which element has 2 protons? Element number 2. What's element number 2 up there? If you squeeze 2 hydrogen atoms really crazy tough, crazy hard, crazy pressure, you get helium. Now, helium has 2 protons, and there's still hydrogen inside the star as well, which is 1 proton. If I squeeze 2 protons and 1 proton together, how many protons will I get? Please do the math. Which is going to create element number 3, which is lithium. This is what's going on inside stars. This is how all of the elements, all of the stuff that made you, comes from the inside of stars through this. And we build up. Oh, you got lithium, 3 protons, and another hydrogen atom, 1 proton. It gets squeezed together under tremendous pressure. What do you get? How many protons? 4. Element number 4, which is beryllium. Or you could even take shortcuts. You could squeeze 3 lithiums and 3 lithiums, and you'll get element 6, which is carbon. This is what's going on inside a star. Up to about iron. It can't form much past iron. It takes too much energy to continue to squeeze atoms and protons together. Because remember, protons are like charges. And what do you remember? Like charges something. Repel. So you need a lot of pressure to get them to stick together permanently. Okay? Back to your notes. All atoms up to the size of iron are formed during the regular life cycle of a star. And then, often, the star explodes in the largest explosions in the universe. These explosions can be so bright that that one star can actually outshine the entire galaxy that it's a part of, the 100 billion other stars. And in that explosion, elements heavier than iron, all the way up to uranium, those are formed during those explosions. They're formed during supernovas, supernovae. In fact, sometimes they're even visible during the day. They're that bright. We haven't had one that bright in about 400 years, but the Trifid Nebula exploded about 400 years ago. You can see all sorts of records of it. The ancients know, hey, I'm seeing something during the day that's not there. It was that bright. You could see it through the blue sky during the day. And we have one right now close to us that's a ticking time bomb. It's due to go off, well, I'm going to say any day or any million years, because on the cosmic scale, that's a small amount of time. You might get it in your lifetime. You would be able to see it during the day. Here's an old picture of me. And you. So where you came, all the atoms in you, here's where they came from. Our story is the story of the universe. Every piece of everyone and everything you love and everything you hate of the thing you hold most precious was assembled by the forces of nature in the first few minutes of life in the universe, transformed in the hearts of stars or created in their fiery deaths, and when you die, those pieces will be returned to the universe in the endless cycle of death and rebirth. What a wonderful thing it is to be part of that universe, and what a story, what a majestic story. It's from a physics prof. Here's another one. Matter flows from place to place and momentarily comes together to be you. Some people find that thought disturbing. I find the reality thrilling. From Richard Dawkins. The life cycle of a star depends on its mass. Put your pencils down. So there are 3 types of stars. Is this going to scroll? No, let's try this again. Come back. Oh, no, I got another video for you too. Sorry, my bad. So there's an old proverb. It says, be humble, for you're made of earth. Be noble, for you are made of stars. Open your textbooks, please, to page 371. There is a lovely color picture on page 371 that I could not reproduce in your notes. So as long as there's one per table, so if you can, put it between you so you guys can share, but make sure you can look at it. Hudson, why don't you move to that side a little bit and you can share with Charbel, and you can sit next to Tristan and you can share. Okay, you need to be able to see this because I can't reproduce it very well. This is a picture on page 371 of the life cycles of stars. And you may notice, if you're looking very, very carefully, that there are 3 pathways. One this way, one down the middle, and one here. In fact, we categorize stars into 3 main types. We talk about low mass, intermediate mass, and high mass stars. You'll notice in your notes, those are the next 3 headings coming down the pipe. You know what? Light, medium, and heavy. And depending on how much mass you have when you're formed as a star, that determines your life cycle. So low mass stars all form from nebulas, stellar nurseries. If you're a low mass star, you become a red dwarf, and you eventually become a white dwarf, and we'll write this out. Intermediate stars, like our sun, once they form, they become a main sequence star, and they last nice for quite a while, which is why we have this kind of elongated path here. And then eventually they turn into red giants, and then they become white dwarfs and black dwarfs. And then massive main sequence star, high mass stars. They become what we call supergiants, and these are the ones that can explode into a supernova, and then whatever core is left behind can either form what we call a neutron star or a black hole. That's what this diagram is saying. Yep.
When we see a shooting star and how it's like bright and it goes out,
yep.
Are we seeing it go?
Shooting stars are not stars at all. All shooting stars are rocks hitting the atmosphere and burning. We're actually going to look at those later on, but they're misnamed. We call them shooting stars because they're bright, but that actually is the star burning. That's the star, the rock burning up in the atmosphere. The same way when you rub your hands, it creates heat. It's hitting the air so fast that the air rubbing against it creates enough heat to burn the rock. I kid you not. Yeah.
What stage is our sun at?
Right around here. We got about 4 billion years before we need to get worried. I don't plan on being around. But around 4 billion years or so, it's going to start to expand.
Oh.
Yeah. Yep.
What's a black hole? Does it actually suck?
We're going to talk about that later, but good question. I have a video. Of course I do. Yeah.
You said that stars form nebulas.
Yep.
How does the sun move away from the nebula?
It doesn't move away from the nebula, but because the sun is sucking things in with gravity, what the sun essentially does is it clears out much of the debris in the solar system, absorbing it. Also, as the planets coalesce, they form from all the dust and gases, and then as they orbit the sun, they clear out their orbital path of all the debris. In fact, that's why Pluto is no longer considered a planet. When we made the definition for a planet, one of the things that we said was a planet had to have cleared its orbit out of all the debris. Pluto has not done that. It's too small. It doesn't have enough gravity to suck everything out. Good questions. What I do want you to notice from this picture, Brandon, is 1, 2, 3 paths. And it's also kind of a nice picture. So let's talk about it in more detail in our notes. You were asking about where our sun is. And so this is a lifetime sequence of main sequence stars. They're nice and bright for about the first 2 billion years, which is 4 billion years. Right now, we think the Earth is about 4.5 billion years old. So we're right about here. We're still good for a while. And our sun is actually going to be okay for a bit. So now we're back to our notes, but you also have the chart. Lowmass stars. This is the top row of page 371. They start small, stay small. We call them red dwarfs. What color do you think they are?
Red.
See, we know how to name things in physics. Are they big or small? What tells you that these might be small-ish? What word?
Dwarfs.
Dwarfs. Okay. We know how to name stuff, not like biology where they use Latin. They burn very slowly. They actually may live 100 billion years or so, and the fact our universe is only about 13.5 billion years old, they're going to be around for a while. We have a fairly young universe. Eventually, they become a white dwarf, not as hot, and then burn out, become a black dwarf. That's that top row. Then we have Intermediatemass Stars. That's the middle row on page 371. So they burn hydrogen faster. They're brighter. They last only around 10 billion years or so. This is our sun. Close to the end of their life, they expand into a red giant. What color do you think a red giant is?
Red.
Is it big or small?
Giant.
See, we know how to name stuff. And it sheds most of its outer material and collapses, becoming a white dwarf, and then as it cools off, because stars get their color from how hot they are, a black dwarf. What color do you think a white... Well, a white dwarf isn't actually white. It's cooler. It's whitish. The sun, Kevin, here's your question, will become a red giant in about 5 billion years or so. It'll expand. The mathematical models, Earth is right on the edge. It might expand and swallow up the Earth, or it might get really, really, really close to the Earth and just burn it to a crisp, but not actually swallow it up. Depends which mathematical model that you use. Pardon me? We would hopefully be long gone and have colonized elsewhere. Or, I mean, we've only been around for a few 100,000 years. What we say is, if the age of the universe, if the length of the universe was a football field or a soccer field, humanity is about the width of a blade of grass. That's how long we've been around. Yeah. We haven't been around along for very long. High mass stars. Huge, and they consume energy much faster, which means they give off more heat and light. Because even though they have more mass, they're burning it so much faster, they live for around 7 billion years, give or take. But there's a huge range. Some of them may actually only last for a few 100 million years as opposed to the billions of years, because they're burning really, 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 really fast. So I wrote here, no, I didn't put the huge range. I just left it in the notes here. They become supergiants. What could you tell me about the size, even though I haven't told you yet, of a supergiant? If you were making an educated guess, what would you say? Big or small? Really big or really small? What do you think's bigger, a red giant or a supergiant? We know how to name stuff in physics. Then they collapse in on themselves, causing dramatic explosions called supernovas, or actually supernovae is the proper plural. One supernova, more than one supernovae. And they can be so bright that they can be seen during the day from the Earth. But we haven't seen one that bright in over 400 years, but we're due. Put your pencils down. The next supernova, Betelgeuse, is predicted to go supernova soon. All the math says it's a ticking time bomb. Now, by soon, I mean next week or a few million years, because on the cosmic scale, that is a snap of a finger. If it goes, we're pretty sure you'll be able to see it during the day. And at night, it would be significantly brighter or as bright as the moon. The night sky would look very different than what it does now. It'd be pretty cool. So, keep fingers crossed.
How long will it stay bright for?
Probably for a few hundred years. You know what? I have to look it up, actually. I should take that back. I know some burn and last for quite a while. Some only... the Crab Nebula, which was once a supernova, I think that one went off in like 1066 or something like that, and I think that was visible for a few years. Many different cultures in their legends and oral history recorded, there's a new light in the blue sky. Where is that from? And back then often they took it as a sign from the gods or whatever. And so there's numerous cultures that have recorded that one. And we can do the math and pick it at a pretty good date. It'd be cool. If the star was about 10 to 15 times the size of the sun, it can collapse into what's called a neutron star. Next set of notes, neutron star. And what this is unbelievably dense. You can imagine something like the size of our sun is so squeezed together that it's only about 10 kilometers wide instead of several hundred million kilometers, or several 100,000 kilometers wide. And because of that, the atoms are really, 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 really smooshed together. I've showed you guys the lead ball that I have, and many of you have picked it up. That's dense. Imagine something billions of times denser than that. So a neutron star that size right there would probably weigh more than the Earth. So imagine something weighing more than the Earth, as big as this thing. I can't wrap my brain around, but that's how dense they are. Oh, I got a little video. Put your pencils down. Oh, answering your question a little bit here. If the mass was around 25 times that of the sun, as it collapses, it can become a black hole. Now, what's a black hole? The gravity from a black hole is so strong that nothing, not even light itself, can escape.
Please
hang on here. Let me pause this.
Could we have all...
So answering your question, all mass acts on other mass with gravity. So the sun has a lot of mass, that's what holds the Earth in its orbit. The Earth has mass, that's what holds you to the ground. Black holes have so much mass, but it's also so compressed together that their gravitational force is strong enough that even light can't get away. We can detect them because we'll look out in space and we'll see light warping and bending, and we know, oh, that was light that didn't get sucked in, but it got curved by the black hole, but it made it out still. And so we can actually see where they are. That's how, because how would you spot a black hole if you can't see light coming from it? How do you know it's there? We see the warping, the curvature of other light around it. We believe that at the heart of every galaxy is a massive black hole. We think that's what, especially spiral galaxies, that's what keeps the stars all spiraling around that central core. And oh, apparently I have a video. Put your pencils down.